Okay, so thank you for coming to this talk where I will talk about histogram support in the upcoming MySQL 8.0. My name is Øystein Grevelen. I work for the optimizer team at Oracle, the MySQL optimizer team. The agenda for my talk is that I will start with a motivating example about why you want to care about histograms. As a quick start guide on how to use it, how are it used internally in MySQL, some example of how you can get better query plans by using histograms, and end up with conclude with some advice. So for the motivating example on the need for histograms, I have this simple join query here. I'm joining two tables, the orders and the customer tables. And I have some where conditions on the date and the account balance of the customer. And if I run explain on this query, you will get a query plan, the plan that the optimizer has chosen in order to execute this query. And what you can see from the output here is that it will start with the orders tables, and then for each row of the orders tables, it will do lookups into the customer table to find the matching row. And you can see which index is used. This one will be using a table scan. And that is because when you are looking for more than 30% of the rows, using an index is not optimal anymore, because you will access so many rows that it's more efficient to just scan through the entire table. We have an index, an order date, as we can see here, but we are choosing not to use it. This estimate you have here on filtering is pretty accurate, because when you have an index, what the optimizer does is ask the storage engine, in this case InnoDB, how many rows are in this range. And what the storage engine does, or InnoDB does in that case, is it takes the start of the range and the end of the range and navigates through the B tree, and then it estimates the distance between the two pages that it finds the start and end row in. And that way it has a pretty good estimate on the size of the range. However, for the other table, the customer table, we don't have an index on this account balance column. So the optimizer does not have any information about the selectivity of this condition. But what it does in MySQL 5.7, it makes a guess. And since this is a range, it guesses that probably 1/3 could be in this guess. But this is just a guess, not something it has any basis for except the type of expression here. So you might wonder, is this really the best join order? So one way to try the difference is to use a hint. And if this was 8.0, I can actually force the join order with this hint. I say customer should be before orders. In earlier versions, you have straight join that can do the same, but then I would have to switch the order here, because then customer actually has to come before the orders in the join query. So this new hints has the advantage that you don't have to edit your query in order to specify the join order. And what I see when I execute these queries is that if I switch the join order, it's much faster. It goes from 15 seconds to 1 second. And the reason for that is that there is no customer that has an account balance of less than minus 1,000. So actually, if you do this order, you will scan through the entire customer table, you will find nothing, and there will be no lookups into the orders table. But the optimizer is not able to know that, because it does not have any information about the selectivity of this condition. And that is where histograms come in. So what I can do, I can say, create a histogram using this syntax, coming back to more on that, on this column. And after that, you see that now it will pick this join order. There's no join hint that's forcing this join order. It picks it by itself because now it knows that the filtering here is 0%. So now you see why the histogram is a useful addition when you don't have any other in statistics on your columns. So a quick start guide on histograms, or I could also call it all you need to know about histograms probably. It's not that much. So histograms is statistics on columns, the distributions of the values you have for your columns. You've grouped the data values into buckets. I will get back to what that means. And for each bucket, you calculate the frequency of values in that bucket. For the histograms, you can have, they have maximum of 1,024 buckets. And when you build, MySQL builds a histogram, it could either base it on all the rows of the table or on a sample of the rows of the table. It depends basically on the available amount of memory you reserve for creating the histogram. And there are two histogram types which are automatically chosen by the MySQL. It could either be a singleton, which has one value per bucket, or an equi-height, which can have multiple values per bucket. I will show you now what that means. If you have a singleton histogram, you have one value per bucket, and for each bucket you store the value and the cumulative frequency for that bucket. Here's an example. You have a set of values between, a column has a set of values, a domain between 0 and 10, and you have like 14% zeros, you have 22% ones, and so on. And this is very useful because since you have one bucket for each value, you can both estimate easily the equality frequency or the range frequency, because the equality will be, as I said, if you have the column equals 0, you know it's 14% in that. That is the selectivity. And if it's like less than 5, you know that is the sum of these 4 buckets gives you the selectivity. And you see, if there's no value, like for 4, there's no value. So there's no bucket for 4 here. So you can also determine, or for values larger than 10. So you can easily determine if a certain value is not in your database. But often you have columns that can take very many values, and then you can't have one bucket for each value. So then we have something called equi-height histograms, which can have multiple values per bucket. And the ones we have implemented, it's not true equi-height, because unlike the basic equi-height histograms, we do not split values across buckets. So because in this case, this is the same values as we had on the previous slides, but now we have only 5 buckets. So we get more than one in each, potentially more than one value per bucket. And you see that a nice feature with the not the quite equi-height approach is that for high frequency value, you get a separate bucket. So for the most frequent value here is 1, and in this case, you actually get a separate bucket for 1. So if you have something like equals 1 or not equals 1, you get a pretty good estimates. But in other cases, equi-height is best for range and not always that good for equality. You take the example of if you have something equals 6. You have this bucket with 5 and 6, and you see that the frequency for this bucket is 13%, so you estimate there's 6.5% of each. But in this case, there was actually 12% with 5 and 1% with 6. So you see that equi-height histograms, when you do ranges, is not that accurate as a singleton histogram. So for these equi-height histogram, we need to store the minimum value, the maximum value, the frequency, cumulative frequency, and the number of distinct values. So how to create or refresh a histogram for a column? You do an analyze table command, but it's a special variant where you say update histogram on a set of columns with a set of buckets. Note that this analyze table command, it will just do the histogram. When you say update histogram, it will just do that. It will not do the other analyze, the normal thing you do with analyze table. And you can drop histograms and columns too. As I said earlier, whether to do sampling or use the entire table is based on available memory, which you can set with this variable. And the default is to use 20 megabyte while creating the histogram. This is about the amount of memory when creating the histogram, not the final storage of the histogram. We have implemented a new storage engine API for the sampling part, which but the default implementation will, even in the sampling case, it will do a full table scan. So if it has only enough memory for 20% of the value, it will read the entire table but just pick every fifth row. But it's possible for a storage engine to implement a more efficient sampling. So for the case, we want InnoDB to implement this in a way that it, instead of reading every fifth row, it reads every fifth page, because that would be much more efficient. The histogram is stored in a JSON column in Data Dictionary. And you can use an information schema table or view to inspect the histogram. So I just specify, I select from the column statistics view of the information schema, and then I specify the schema name, table name, and column name to get the histogram for a specific column. And then you will see something like this. You will see the buckets. In this case, the histogram type is a singleton, so there will be two values, the value of for the bucket and the cumulative frequency for this bucket. You see they are increasing all the way to 1 since it's a cumulative value. You see the data type, how many null values there are for this column. The collation ID does not matter when it's integer, but if it's string, it tells you how it compares values. When you last updated the histogram, so there's no automatic update. So you need, if you want to refresh because your values have changed or something, you need to do another analyze table command. Here you can see the sampling rate. So what you could do if you want to have a full full histogram over the whole table, you can say, oh, it used only 20%. Let's increase my memory usage to go to 100 megabyte, and you can sample the entire, or you can base it on the entire thing. And the number of buckets specified, I forgot to mention that on the syntax. You have this with and buckets where you can specify how many buckets used. And this part is added because when you do a MySQL pump or dump, it will actually put the analyze table commands into the dump file, so that when you run it, load it again, you will actually get recreated the histograms. So that's why it stores the original specification. Because if this is a singleton, it's like here, it only have 7 buckets. But if you specified it with 1024 and the data has later changed, you wanted to have it to still be a singleton, for example. And we can use this information schema. Now, first for strings, you consider maximum 42 characters. So if you have very long strings, and they all have the first 42 characters are the same, then this is kind of not the best. And they are base 64 encoded. This is because what is stored in data dictionary or in JSON in general is UTF-8. But you can, in theory, have any character set here. So it's not necessarily valid JSON, valid UTF-8 character strings that you are storing. So you have to decode them in order to see strings. And there's what I would think is a bug. I think we will fix before GAs. There's some prefix here that should probably be hidden from you. So, but the basic thing here is that I use the JSON table function in 8.0 to convert these histograms, or the buckets array, into a relational table. So this way you can get the table over the values, and you can see here the cumulative frequency. But if you want to see the actual frequency of each bucket, you can use a window function, as Sergey talked about earlier. You take the value of this bucket, and then you subtract the values of the previous bucket. That was the lag function. It refers to the first previous in this case. And since I know this array is already sorted, I don't need something in the over clause here. And that way you can actually see that we have, for this order status column, we have 48.6% Fs and 48.8% Os and just 2.6% Ps, for example. And that's a typical column where you want a singleton histogram, because whether if we have something equals F here and you optimize that without a histogram, I think this is really selective. It's not, because it's like 50% of the rows have this value. So how are histograms used? The most important use case is for when the optimizer want to optimize join queries. Because I see we do something on the first table, and then there's some filtering here, and what's left goes into lookups into the next table. And it's this filtering here that's important to know, because then you would know how costly is this next step. So if this probably one of the major issues with many query plans is that the optimizer does not get the cardinality right here. It does not estimate the effects of the intermediate steps of a join. And there are, as I've already touched upon, several ways the optimizer gets these estimates. In MySQL 5.7, it could base it on the range estimates that I talked about earlier, the way you do deep dive or dives into the index and then you compute the distance. There's also index statistics, what you get with the normal analyze command, table command. And we added in 5.7 some guesstimates here that said that if it's equality, it's 10%. If it's some less than, and so it's 1/3 and so on. Just to have some estimates here, because some filtering is better than no filtering. Often, if you have one table with some filtering and one table without any, you would prefer to start with the one with some filtering. What's different now is that you have histograms here. Still, the range estimates are the most accurate, but histograms is much better than guesstimates. And this is why histogram is not that important in MySQL as in many other databases, but because most databases does not do this range estimate using an index. So the use of histograms is mostly in MySQL for columns where where you don't have an index. So you can then have different ways of getting estimates here. You have the range estimate for this column here if you have an index, and then this equality you can use another kind of statistics, and then you have these guesstimates if you don't have histograms, and then you compute the total here is, if we assume that they are not correlated, this condition, so you compute the selectivity by multiplying the different here, and then if you add histograms here, you see that if you look at this 1/3 for age greater than 21 for employees is probably not a very good estimate. But since an optimizer does not know what the word employee or age mean, it needs something to guide it, and that's the histograms in this case. So it actually happened that 95% of the histogram of the employees are older than 21, and that means that the selectivity computed here goes up from 0.01 to 0.03. And then here you see we still have a one that is a guesstimate, and 10% is probably too frequent, even if John is a frequent name. You could add a histogram here too, but it's not necessarily that good, since you probably have too many names to make a singleton histogram, so the equality will probably not be that accurate computed. So in this case, you probably should add an index or name, because if you look at these conditions here, it's actually the name that is the most selective one. So actually, in this case, you probably will want to start with the employee table and filter out on name using an index. The other ones here is not that selective, and so an index might not be useful, and then you could use a histogram instead. Here's an example of how we use histograms. This is still an age column, and in this case it's not employees but the entire population. So you see there's an equi-height because you have 10 buckets, and it's around 10% in each of the buckets. And most of them are like about 7 or 8 years in each bucket, except the last one, that for natural causes is a bit wider in range. And we have stored, for each bucket we have the cumulative frequency stored. And to show you why this is most useful, I can go through an example here where we are looking for all that are 21 years and below. First we do is we identify the bucket for 21. It's this one. Then to compute the selectivity, we first check the cumulative frequency of the previous bucket, which is 20.3%, which is, and all these, we know that these are younger than 21. And since we have the cumulative frequency here, we don't have to check the frequency in this bucket. It's enough to check the previous one. We know that we have at least 20%, but then we need to figure out how large part of this bucket should go into this condition. So then we check the frequency for that bucket, but then we need to take into account that 21 is like less than or equal to 21 is like 5 or 8 of 8 values in that bucket. So you add that fraction to the selectivity, and you end up with 0.267 as the filtering effect of this condition. And if you want the opposite, you just do 1 minus the previous one, so you get that 73% is older than 21. Another example of a query, this is a query from the DB3 benchmark, where you have, I don't want you to, you don't need to understand the entire query. It's called a volume shipping query, and actually what it does, it calculates the revenue of goods going from suppliers in Russia to customers in France and vice versa. And we don't have an index on the name. And as I said earlier, if we would be guessing, we would say that 10% would be Russia and 10% would be France, which probably is not accurate, because neither Russia, there are more than 10 countries in the world. Without histogram, we get this plan. We start with a full table scan, or one normal join plan. Start with a full table scan or a range scan, and then you do lookups into each table, either a secondary index or a primary index, all the way to have chained together all the tables. In this case, that means that you get like 855,000 primary key lookups into the other nation table. But when you add Histogram to this, you see that there's very few combination here. So actually it's better to just combine these France and Russia early on, and then you avoid thousands of primary key lookups in the final table that you will otherwise have. And if you look at the performance here, we see that not as big as improvement as in the first example, but you see that you go down from 1.7 to 1.35 seconds or something like that. So to conclude with some advice here, when should you create histograms? It's useful, as I said, for columns that are not indexed, or for columns that are not the first column of any index. Because if you have like a two-column index, there's no way for the optimizer to do this index dives in order to find the values for that column. And it's used, in addition to join queries, which is the most important, it's also useful for queries where you have in subqueries, because there we try to estimate the size of the subqueries and so on. And also for single table queries, if you have order by limit, because then you have the choice of ordering the entire result and then do limit, or use some index that are already ordered. But in order to understand whether that is performant or not, you need to know how far into the index do you need to scan in order to find enough rows for your limit. And then the filtering estimate is important. The best fit by far is if you have low cardinality columns like gender or order status or day of week or so, because then the okay, I have to end, he says, but I only have this one left. If you have an index, no use. If it's not used in a where clause, forget about histograms. How many buckets? If you can get a singleton, use as many as you need. If not, I would guess 100 should be enough, because then you have like a granularity of 1%, which should be useful. More information, there's a nice blog by my colleague about this that you can look up. The slides are already on the FOSDEM page, so you can get all that information from there. Yeah. Show me.
Do histograms persist a server restart?
Yes, it's stored in this in data dictionary, and it's what the new 8.0 data dictionary made it very very easy to make a information schema view over this, and they got a lot for free by using that. Yeah. So how is using histograms, how would that differ from partitioning? So you want equal size partitions in some way? Yeah. Okay. We haven't thought about that, but one thing I forgot to say is that if you have histograms, they are good estimates of your data, so you can actually, instead of doing costly queries against your data, you could actually just query the histograms in order to get the and you can use that. You can use the information schema table for. Yeah. Yes? No, we don't currently have that. In order to detect whether to update a histogram, I guess you need to to keep have some awareness about how frequently your distribution change, because like in this order status example I had, for example, they are usually pretty fixed. Even if you add more orders, it will probably be like 47% of each of the two big ones and 3 in the last one. So in that case, you would not need to update your histograms even if you add a lot of more data. In other cases, that might not be the case.
If you have more questions for Øystein, go to the bar with him, pay him a beer, he'll be very happy, and it will answer your questions.